So you could see now? Yes, you could see now, right? So this was my original slide when I talked. So this is my outline, and this is my first slide. So it's okay now, right?
Okay.
You're able to see, yeah. So yes, so the standard model, so basically the standard model of particle physics encapsulates most of the things that we know about particle physics. It unifies strong, weak, and electromagnetic interactions. It doesn't have anything to say about gravity. And it comprises the matter fields, quarks and leptons. They each come in 3 families, and quarks participate in strong, weak, and electromagnetic interactions, whereas leptons don't have any strong interactions. And the bosons are the carriers of the forces. The photon for electromagnetic interactions, the gluon for strong, the W and Z for the weak interactions. The Higgs is the odd one out. This is a scalar field introduced to give masses for both fermions and bosons. And of course, if there was gravity, the graviton would be a mediator of this force. In addition, there are some fundamental symmetries that describe this model, and they favor left-handed doublets over right-handed. So this is one. Okay. Okay, you can still see it. All right, so this is not really understood. The standard model has some shortcomings, perhaps both in experimental and theory part. And so we're trying to deal with getting some answers for some of these questions left unanswered. So one of them is the question of parity and neutrino masses. There is also the question of dark matter. So this is what these left-right symmetric models achieve. Now there is a standard left-right symmetric model which deals with parity and neutrino masses, but the drawback of this is that it expects the additional particles in the model to be very high, because if not, they would break flavor changing neutral currents. And also this model doesn't have any dark matter candidate. So this is what led us to look at this alternative left-right model. I should say that we didn't come up with the idea. The idea is of Professor Maz and Professor Khalil, and his student developed a model in much more detail. So we are following in their footsteps. So where does it come from? So the idea would be that we would like to have a grand unified model. So this would be a model that would unify not just weak and electromagnetic interactions, but also the strong ones in one big model, which is this gut grand unified theory. So in our case, this would be E6. And from breaking of E6, we could get either this left-right, the ordinary left-right symmetric model, or the alternative model. So you could see that this alternative model has an SU2 right prime. In other words, the quarks and leptons are both left and right-handed are in doublets. However, the partner of the right-handed up quark, so the SU2 right prime up quark is exotic. The partner is exotic, and the partner of the right-handed lepton is also exotic, and we call this is a neutrino type, and we call it a Scottino. And then, of course, we do have some singlets. So this is a field composition of the model. So we have, you could see for quarks, we have the ordinary doublet U left and D left. And then for the right-handed, it contains the ordinary U right and then this exotic quark. And then the missing particles D prime left and D right are singlets. It's the same thing in the lepton sector, but we now have this field, the Scotino field, which is a right-handed partner of the right-handed electron. In terms of the Higgs fields, we have this, as in the normal left-right model, we have a bi-doublet Higgs field carrying both left and right quantum numbers. And then we have doublets, left-handed and right-handed Higgs. These are all needed to break the symmetry to the electromagnetic group. And so we have, of course, the gluon, the left-handed W, the right-handed W, and the U1 B minus L field B mu. In addition to the SU3 cross SU2 cross U1 quantum numbers, and groups, we introduce this other group U1S. So we introduce an S symmetry, and so the S symmetry is introduced so that we can introduce a generalized lepton number. This would ensure that the exotic fields don't mix with the ordinary fields. But this, of course, means that some of the Higgs would have this generalized lepton number. Now, this is not a normal lepton number. So we can write then the Yukawa interaction that is consistent with all the symmetries. And as I was telling you, the symmetry breaking occurs through the vacuum expectation values of the bidoublet. Notice that the bidoublet only the phi to 2 gets a VEV. The other one does not get a VEV, and this would allow W left and W right not to mix. And in addition, we have VL as a VEV for the left-handed doublet and VR as a VEV for the right-handed doublet Higgs. With this, we have mixings in the charge sector, and notice that it's very interesting that in the charge sector, we have phi 2 plus minus and chi L plus minus mixed separately from phi 1 and phi R. And the results from each of these mixings is a charged Higgs and a Goldstone boson, which will be absorbed by the charged vector boson. So G1 plus minus by WL and G2 plus minus by WR. And then, of course, we have a 4x4 mixing matrix for the pseudoscalars and a 4x4 mixing matrix for the scalar neutral Higgs. Perhaps interesting here are the gauge boson masses. I was telling you that W left and W right do not mix, and this is a big advantage of the model because W right doesn't mix with W left. It only decays into one ordinary quark and one exotic quark, or same thing with leptons. And thus it actually can be light because it's not directly, its mass is not directly restricted by any constraints. However, in the neutral sector, the gauge bosons mix as usual. So all three mix, and so we would have, so I have exact masses for the ordinary Z boson as usual, and for the additional Z boson corresponding to well, it's a mixed, but corresponding to the introduction of SU2R prime. So the Z prime boson would be, its mass would be restricted by collider phenomenology. So indirectly, this would restrict the W prime or W right mass. So we don't have direct constraints on W right, we have indirect through the mass of the Z prime. In addition, we have masses for all the fermions, including the exotic D prime and the Scotino. Notice that they are all independent of each other, so we can fix them separately. Here I'm writing the one family mass, but it can be generalized easily to 3 families. Now, what is interesting with this model is that we are able to introduce an R parity. Now, for the people who's familiar with supersymmetry, which is another beyond the standard model approach, this R parity distinguishes between particles and superparticles. Here we're going to distinguish between some ordinary particles and some of these exotic particles. And as very much like in supersymmetry, introducing this would allow us to have a natural dark matter candidate. So remember when I was talking about mixing in the charged Higgs sector, I was showing you how the two, we have 2 blocks of mixings the 2 blocks don't speak to each other. This comes from this natural generalized R parity. So I've given the R odd parity under this definition. So here, B baryon number, L lepton number, and S spin. So of course, fortunately, all the rest of the parity, the other particles, including, fortunately, all the ordinary particles from the standard model are R parity even, and we have some R parity odd particles, some of which, the ones that are neutral, would be a good candidate for dark matter. So of course, this would mean neutral Higgs, pseudoscalars, or Scotinos, since dark matter has to be charge neutral. So what we're going to do is look at the possibilities that either the neutral Higgs, the pseudoscalars, which are very similar, so we have only one investigation, or this Scotino would be a dark matter candidate. So we want to explore this now. So the scalar particles that are candidates for dark matter are H10 and A1. These are both R parity negatives. They're degenerate in mass. This is a mass in terms of some of the parameters in the potential. We want to see, so we want to scan over a certain parameter space to see whether this would make good dark matter candidates. I should say that in addition to these 2 masses, these 2 Higgs, the charged Higgs H1 plus minus and H2 plus minus would be important. One of them is R parity even, the other one is R parity odd. The R parity odd can be quite light, and so in principle could be the neutral R parity odd scalar and pseudoscalar. So when we talk about dark matter, we want to compare with the constraints for dark matter coming mostly from the relic density, which measures how much dark matter we still have in the universe, and from direct detection. So there are very stringent limits on detecting dark matter particles. So here I'm showing for the case in which the neutral Higgs is a dark matter candidate. The possible annihilation channels. So remember, we would be producing dark matter candidates in pairs, and depending on their masses, they can decay into various channels. So if the mass of the dark matter candidate is less than the mass of the standard model Higgs, 125 GeV, it could decay into either gauge boson pairs or BB bar. If the mass is between the mass of the Higgs and the mass of the top, it could also decay into Higgs pairs. And then, of course, if it's higher than the mass of the top but lower than the mass of the R parity even, it could also decay into TT bar. And of course, if it's greater than the half of the mass of the charged Higgs and the W bosons, it's a combination of W plus minus H1 minus plus opens. Now remember that I'm looking at this in particular because these are R parity even states W H1, so then we would be able to find them. So for the numerical study, so we found that the some parameters are very sensitive to our numerical explorations. Some parameters are not. In particular, alpha 1, alpha 2, alpha 3 are not very sensitive. And tan beta is more sensitive. And lambda 2 not particularly sensitive, but we need to fix some parameters. And so we vary the rest of the parameters in the ranges specifying the table on the right-hand column. Now mu3 in here would always have to be negative for vacuum stability. And so here, remember, Q prime is the exotic quark, and then we have the lightest tau Scottino, the lightest Scottino, the tau Scottino, and so we vary the mass differences. So we found out that there is a very big difference, or at least a significant difference between whether we consider the Scottino, so remember these are the other R parity negative states, to be degenerate, to have small splitting in mass, or to have a large splitting in mass. So we're going to look at these three cases separately, and we will differentiate them by different colors. So for us, small splitting is between 10 and 20 MeV, and large splitting between 100 MeV and 10 GeV. So here first, we're looking, in the first figure, we're looking at the relic density. So we have the degenerate case in which there's no splitting between Scottino is kind of a olive green. The small splitting case is a darker green, and purple represents a large splitting. And so we follow this on all our plots. So you could see that the relic density, which has to, we show it within a 1 sigma, it has to be between these two horizontal lines, has a fair bit of points consistent with it. When we look at the direct detection constraints only, we find out that the large splitting cases dominate. But however, if we want to constrain all cases by constraining both the relic density and the direct detection cross section, this is at the right. So we do get some points for all, and you could see that the mass of the dark matter MH10 can be fairly light. And so below, we just show the cases for indirect detection, and we show them separately for the degenerate Scotino case on the left-hand side, small splitting in the middle and large splitting on the right. And the black points also satisfy direct detection and relic density constraints. And you could see that we get a fair bit of points in all cases. And again, what is good is the mass of the scalar dark matter can be very light. What about if instead of the scalar dark matter, we consider the case of the fermion dark matter? And so we look at the tau Scotino as being the lightest, and the possible annihilation channels for this are into leptons or neutrinos, quarks, gauge bosons, and then gauge bosons plus Higgs. So we vary the mass of the Scotino again in this 100 to 2000 GeV range, and the only other parameters that enter our calculations are the mass splitting between the Scotino and the exotic quark, and between the neutral and the R parity odd charged Higgs. This is a vacuum expectation basically of the associated with SU2 right prime. And again, we're looking at a case in which we have degenerate Scotinos. We always take the electron and muon Scotino to be degenerate, but so when we talk about degenerate small splitting and large splitting, we talk about splitting with a tau Scotino. And we use the same parameters as before.
May I interrupt? May I kindly remind you about the time?
Yes, how much more time?
Just a few minutes, 2-3 minutes.
Okay, so I'm not going to talk about collider. I'm just going to finish with the relic density just to show you what we get for the Scotino. So again, we're looking at the relic density, the direct detection, and the indirect detection. So the only things that I want to point out here is that we do have a fair bit of points, but unlike the case of the scalar case, the mass of the fermionic dark matter has to be basically higher than about, we do get some points in the lower region below 1 TeV, but these points most of them don't survive the direct detection cross-section, and none of them survives the indirect detection restrictions. So I'm not going to talk about, I do have a couple of slides, I had some slides to do with looking at the collider, and all I can tell you is that we have a good chance to see them at collider with good significance, but I'm just gonna conclude by talking about the advantages of this model. We have additional Higgs and W right bosons that are light. We can get dark matter by allowing this R parity symmetry, and we could have both scalar or fermion dark matter, and they are all consistent with the relic and direct and indirect bounds, and whether the scenarios include degenerate small or larger splitting among the Scotino dark matter candidates. Thank you.
Thank you very much for your contribution. Let me see whether we have any questions or comments.